This meeting is being recorded.
Okay, very good afternoon. Screen is visible.
Yes, sir.
Okay, so today we are actually going to have hands-on on this microwind software, right? This software which we can use to design and simulate different CMOS logic circuit. Okay, whatever the different designs, different logic designs, maybe a combinational or sometimes sequential that you can design using CMOS, you can design by using the CMOS design rules, and you can simulate the design, okay, to check the output. So first we will look the introduction to this tool, or you can say software. What are different options, what are different uh, tabs, right? What are different options the software provided to us. So basically this is a front window of this micro wind version 3. So on this menu bar you can have different options. First one is a file open, then save, this is a drawbox, this is a delete. Okay, this gun type symbol is of course of delete, this copy elements, this stretch and move. That means if you want to move particular element, okay, then you can move this. This is a zoom in, this is zoom out, this is view all. That means if you want to see your entire design into a single screen, you can choose this option. Then this is a simulate, run simulation. These options you can use to measure a distance, right? Because see, we have different design rules, set of design rules, right? Whatever the minimum distance of n diffusion region, then metal, polysilicon, everything that we have already discussed in unit number 2. So to check whether we are following and whether we are uh, whether we are following and obeying the design rules, you need to have this scale, right? Like this. So this scale will tell you that yes, you are obeying the proper design rule. Okay, so you can plot this scale and you can check the distance and all that. If you want to delete this, select this delete, select this box, select this box, it will get deleted. Okay, now this scale, okay, let me clear this. Okay, let me reopen. I don't know what problems occurs. Okay, there may be some problem. So this scale you can choose to measure a distance. Then you can have this 2D vertical cross section. Then you can have this 3D view. Okay, so whether you can actually build and different design process steps. So this initial substrate, right? Then next is the end diffusion. Okay, this end diffusion. Then you have SiO2 stretch. This is a thin oxide reduction, then polysilicon. So different design rule and design step that uh, you can watch here, or you can see here in the 3D, three dimension. Okay, so this is option by this 3D. Now next to that 3D is a design rule checker, DRC. So what is use of this design rule checker? So whatever the design that we have built, right, if that design is within the design rule or not, to check that, or you can say to compile that, you have different design rule checker. Okay, this a add text box. By using this you can add different text label, you can label some PMOS and MOS, or if you want to give some label, you can add label also. Then this is a palette. Now this is a very important tool for us. This is palette where whatever the different options, right? So these different options will come into this palette and you have to choose particular option and you have to drag here, okay, in this p wheel, okay. And this is a left side move, right side move, bottom move, top move, okay. If you want to move your design at the top side, this one is the option. Bottom side, this one is the option. This is left side, this is right side. So depending upon your requirement, you can move the screen, okay. Now coming to this palette, okay, what are different options you have in this palette? So first you have a CMOS or MOS generator, then you have a complex contact, then you have a virtual capacitance, resistance, this is inductance. Then first one is a VDD supply, this one is a high voltage supply, this is a ground, this is a clock generator, this is a pulse generator, this is a sinusoidal, right? And this is a visible node. That means output you can check through this visible node. Then these are the different layers of CMOS. By using these layers and contacts, you can design this, right? So this is a metal 6, metal 5, metal 4, polysilicon 2, right? This is a p-type diffusion, n-type diffusion, this is a n veil, this is polysilicon. So you can go for a different option. So now we will have one design so that you can easily understand how to use this tool, okay. So first we will design very simple design of our CMOS inverter, right? Now all of you are aware of what do you mean by CMOS inverter. You have a PMOS as a pull-up network and NMOS as a pull-down network, right? So gate of PMOS and NMOS are shorted and we are providing input to the gate, and from the drain we are making common of PMOS and NMOS and we are taking output from the drain terminal. Now to the source of PMOS we are attaching the VDD supply, and source of NMOS we are attaching the ground, right? So we will start with the design. So first you have to go to this select foundry. Then after select foundry, you have to choose this 0.25 rule, open. Okay. So now it will show that 0.25 rule. Now how to start? Now first you have to decide how many PMOS and NMOS you are requiring, right? How many PMOS and NMOS you will be requiring. So to design a CMOS inverter, you require one PMOS and one NMOS. Now go to this MOS generator. Okay. First you have to get the NMOS, right? You have to get the NMOS. So now you can see here, you can choose in microns this length and width, or you have another option of this lambda also, right? You are having another option of lambda also. So you can choose this 10 lambda, or maybe minimum is 4 lambda. So you can uh, keep 4 or 5, no problem. Generate this device, okay. Generate device, you can click here. Yes, now you will get this as a NMOS. Now this is about NMOS. So what is specification of this NMOS? So I will explain that. First we will get the PMOS also. So similarly for PMOS also, you can keep the same width, same blend, generate device, click on this anything, anywhere, you will get this PMOS, right? Now what you can see here, so this red polysilicon is the gate of PMOS. Okay. And regarding the drain and source, in case of this microwind software, so you can make or you can consider any of the this terminal, this blue terminal as a drain or source, right? But this red one is always gate. This is fixed one. So you can consider this left hand side one as a drain and this one as a source, or you can consider this one as a source, this one as a drain, doesn't matter. Similar is the case with this PMOS also. This red polysilicon is gate, it is fixed one. Then this one is a source or drain, or this could be a source or drain, depending upon your consideration, you can see. Now, by using this stretch symbol, you have to select this and you can move this exactly above the PMOS. So you have to maintain a proper distance. Now, first, what we have to do, we have to short the gate of both and we have to provide input there. So gate is made up of polysilicon. So you have to select the polysilicon from this. You have to exactly match this gate terminal, right? You can connect over here. Yes, now it is shorted, and you have to this extra part here, you can apply input. Now the gate of PMOS and gate of NMOS we have shorted, and we have get an extra terminal so that here we can apply input. Okay, now this is done. Now what's next step of design is, we have to connect the VDD and ground terminal. Okay, so you have to VDD, we have to connect this, so this will become a source, this will become a drain of PMOS. In the case of NMOS, this will become a drain and this will become a source, because we have to short the drain terminal, we have to take the output, right? So which one is closer? So you can consider that terminal of PMOS and NMOS as a drain terminal. Okay, so first now we will connect this drain terminal over here. We have shorted this and we are taking output from here. Okay, now this is a drain of PMOS, NMOS we have shorted and we have taken the output. Okay, this is fine. Now next is what, we have to provide a VDD and ground. Okay, so we will just extend this terminal. This is a source of PMOS. Here we will apply VDD and here we will apply ground. Okay, so this is done. Now how to get the VDD and ground from this palette? So here is option VDD supply. So click on this, connect here VDD. Again click on this, you have to give VDD to NVEL also. See, in case of this micro wind, so for,
Excuse me, sir.
yes,
Screen is not visible.
okay, I will again reshare one. We just wait. Okay, now it is.
Yes, it is visible.
Previous part is you are through with that, or
Yes, sir. The screen is visible, but when the VDD is we are applying at that time, screen
okay,
is
okay,
not.
that time only. Okay, but rest of the parts you have seen, right?
Yes, sir.
Okay, fine. So here from this panel VDD supply, you are taking VDD, place over here. Then again to the NVEL also. See, now you will think, okay, for PMOS you are applying this NVEL. Now, sorry, for PMOS we are giving this NVEL. Now about NMOS, where is a PVEL? Right? Where is a PVEL? So the answer is, the entire background itself is a PVEL in case of NMOS. म्हणजे बघा, आपण PMOS साठी इथं तुम्हाला ही NVEL दिसते, कारण NVEL मध्ये आपण PMOS बिल्ड करतोय, राईट? तसं तुम्ही विचार कराल की NMOS साठी मग PVEL नाही का लागणार? आन्सर इज यस. मग ती PVEL कुठे आहे? तर त्या केसमध्ये ही जी मागची बॅकग्राऊंड आहे, itself is a PVEL. So we need not to add any extra PVEL in case of NMOS, right? So we have applied VDD to the source terminal of PMOS as well as to the NVEL. Now we will connect this ground towards this source of the NMOS. Okay. Now what else is remaining? We have to apply input. Okay. So choose add clock. Okay. Plus here give delay symbol is nothing but the visible node, so you can apply here. You can mention it as a output. Okay, assign, this is the output. Okay, this is the input, this is a output. This is a VDD supply VSS. Now our entire design is correct. But before proceeding to the simulation, we have to first check the design check rules, right? Before proceeding to the simulation, we have to check the design check rules. So we have to click here. Nothing is shown. That means what? The design and distance, whatever you have maintained, it is proper or it is correct, right? If, for example, see, I will make one mistake here. Uh, so if in maybe a next part, I will show you how this design check rules will show the errors or mistakes that we have made into the design. But now we have made nothing. So it is showing nothing. That means our design is foolproof. There is a no design rule error. Okay. Now the next part is we have to simulate this. Okay. How to simulate this? Click on this simple run simulation button. When you click, you will get this simulation. So now you can vary the this delay, you can remove. Okay, then simply click on the reset. Okay, now you will get the simulation. Now we are talking about the inverter, right? CMOS inverter. So what will be the expected output of CMOS inverter? This is the input, this is the output, right? So for 0, you should get 1 as output. For 1 input, you should get 0 as output, right? So this bottom line is a 0 and upper line is a high input. That means 1. In similarly here also, this bottom line is a 0, upper line is a high input. So see, 0 1 1 0 0 1 1 0, entire cycle will show the exactly corrected output. Clear? This is how you can design and build different CMOS logic circuits. So in our next experiment, we are going to discuss the NAND and AND gate, right? Okay. So now through this simulation window, see, you can check the voltage versus time. This is a voltage versus time graph. You can check the VTC curve. This one, VTC, right? This similar curve we have discussed in the theory part also. This is a region first. This is a region 2. This is region 3. This is region 4. And this is region 5. These are the 5 region of CMOS VTC curve. And this middle one is the sub threshold voltage, right? If you click here, this middle one is the sub threshold voltage. Okay, this is VTC curve of CMOS. असेच कॅरेक्टरिस्टिक शिकलोय का नाही आपण? म्हणजे प्रॅक्टिकली आणि थिअरॉटिकली मॅच होते का नाही? राईट? This is a voltage transfer curve of CMOS inverter. You can have the frequency versus time also. You can have the I diagram also, right? This is the I diagram of the CMOS inverter. And this is our normal voltage to time. Okay. 0 1 1 0 0 1 1 0. This is a CMOS inverter. Have you clear with this?
Yes, sir.
And you can save this design also. How to save the design? Go to the file option, click on save as. Okay, give the name CMOS inverter. Okay, save file. The file is already accessed. Will you overwrite it? Say yes, it is overwrite. Okay. Now we will go for design of NAND and AND gate. Okay. So till time we will require this inverter for our future use. So we will just put it over here aside. Okay. Now we have to design a NAND gate. Okay. So uh, just wait for a second. Stop sharing. Where is the option of setting background general. That whiteboard is where to get that whiteboard? Anyone have that any idea? Do you know where to get that whiteboard and all? In the previous it was showing the option, but here it is not showing. I don't know what is the reason. Mm, there may be some option of whiteboard where it is polls, security video, mute. Whiteboard option should appear, right? I don't know why it is not. Here is anything whiteboard? No. Okay, anyway, let me share once again. So now
So we can use the paint, and in that we can draw.
yes, I'm doing that only now. Mm, I have only that option. Okay, let me share again. So see, we will talk about the NAND gate. Okay. Screen is visible, right?
Yes, sir.
Okay. So what is equation for NAND gate? Output Y is equal to
A dot B bar.
A dot B bar. Correct? This is the equation of NAND gate. Now, first we will draw the stick diagram of the NAND gate also, and from the CMOS design, we will draw the stick diagram also. So first we will design this NAND gate using CMOS. Now what is rule for our design? So here is a PMOS. Here is a NMOS. This is a dot product. And this is a OR product. Okay. Now tell me, in case of PMOS, if you have this dot product, okay, which operation or which connection we will prefer, series or parallel?
Parallel.
Parallel, very right, parallel. And in case of PMOS, if you have plus, then we will choose the series connection, right? Exactly reverse is the case with NMOS. In case of dot, we will choose series, and in case of OR product, we will use parallel. Okay. Now remember this thing, because this will require to design a entire gate. This is very important. Okay. Now we will start with the design. Okay. So as first we have to design a PMOS, because see, whatever the you can say CMOS, right? This CMOS, it is made up of what? The PMOS and NMOS, right? This is PMOS and this is NMOS, right? These are the inputs, these are the inputs, and from here it is output. So this is, and these are the inputs. Okay, this we have connected to the ground, and this we will connect it to the VDD. Clear? This is a structure of PMOS. So in this same context, we have to design this A dot B. Okay, we have to design this one. Okay, now first we have to design a PMOS. Now first consider this, as it is a dot, right? So which connection we will prefer? Parallel, right? Which connection we will prefer? Parallel. And how many PMOS you will require? So you have A and B, two inputs. That means two PMOS we will require, and that we have to connect in parallel, right? So, so the same we will transfer here. So the first, this is a VDD. Okay. This is a first PMOS. This is a second PMOS. Okay. This is A. This is B. Okay. You have to connect this part also. Okay. This is this entire PMOS part, right? This entire PMOS part. As it is a dot, right? We have to connect this is in parallel. Now next, where we are taking output, right? In between PMOS and NMOS. So here we have to take this output Y. This is the output Y. Now we have to design this NMOS part, right? We have to design this NMOS part. Now how to design the NMOS part for dot product, and in case of NMOS, how we should connect this in a series, right? We should connect this in a series. That means A and B NMOS we have to connect in series. So let us connect in series. This is first one. This is second one, right? This is A and this is B. And of course, we have to connect this to the ground. This is C, and this is NMOS. As it is a dot product, we have to connect it in series, and as it is a PMOS, we have to connect it in parallel, right? Now, how to draw the stick diagram from this design? Okay, how to draw the stick diagram? So I will draw it here. Let me select this. Yes, where it is, rectangle section. Okay. I will draw it over here, stick diagram. Okay, now first tell me what are rules to draw the stick diagram? Which color codes we are using to draw the stick diagram? Which color code we are using to draw the stick diagram? Metal, it is represented by a metal, it
Blue
is
color.
represented blue color, very right. Then P diffusion, it is represented by
Yellow color.
yellow color, very right. Okay, now first we will choose this blue color. Okay, okay, this is what VDD, and this is ground. Clear? Now P diffusion, it is shown by yellow color. This is P diffusion. And N diffusion, it is represented by, this is N diffusion. Okay, now we have to uh, give the inputs now. Okay, inputs, it is represented by red color. So how many inputs we have? A and B. So you have to place here two red lines. This is A and this is B. Okay, so for your convenience, I will just write here, this is A and this is B. Clear? Now we have to make the connections, right, using this as per this diagram. So first we have to decide the source and drain of CMOS. So how to decide the source and drain? So I will choose a bit different color so that you will not have, I will choose to represent. So this is the source terminal. This is also source terminal, right? This is drain terminal. This is also drain terminal. This is also drain. Okay, this is source. This is drain of this BCMOS, and this is again source. And this, you know, these are the gate terminals. This gate, this is also gate, this is also gate terminal. Now we have to connect this, right, as per the this diagram. This is source. Okay, now source of the this both A and B are shorted and connected to the VDD. Now we will, this is the source of A, this is a drain of A. Now here we will make, this is a drain of B and this is a source of B, and these red lines are the gate terminals. Okay, now we have to make this drain terminals shorted. This is A and this is a source of B. Okay, we made this connection. This part we made. Now, this drain are already shorted. We have got the drain of this already shorted. Where to connect this drain to the drain of A? This drain of, now this is a type P NMOS. This is a B NMOS, right? So we have to connect this drain to the this drain of this NMOS, right? And there we have to take the output also, right? So this is again A, this is B. Okay, now this B, source of B, we will mark here, source of B. Sorry, I will choose different color. Okay, this is a source of B. This is a source of B. This is a drain of B. right? This is a source of A. This is a drain of A. See, you can choose this drain and source terminal as per your requirement. Okay, just a minute. Just hold on. हाँ बोलो ना. हाँ टाका तुमच्या एवढाच. अमोलचं कॉपी करा. कोणाचा बघा की काय काय कोणच दिल नाही. नाही मी विचारून टाकणार आहे अमोलला, मग झाल्यावर लेक्चर झाल्यावर टाकतो. हम्म. Okay, concentrate here. So you can see, you can choose this drain, this source, or this source, this drain. But see why I'm making this arrangement, or why I'm choosing or why I'm taking freedom to choose anyone as a drain source, because we have to make a design simple, right? We have to make the design simple, and that's why I am choosing the drain and source as per my convenience, so that the connection will be easy and it is easy to understand for you also. Okay, so now this both drain of this PMOS, it is connected with the NMOS. Okay, so first I will make one contact here. Now this drain, okay, of it is connected with drain terminal of this one. Very clear. And from this terminal only we have taken the output, so you can extend it over here, and this is your output. Now what remains? This drain, this source and drain we have got already shorted because they are on a same path. And now the last connection is this source of the B. This is a B and this is source of the B. We have to connect it to the ground. So just make one connection and you have to connect this to the ground. Okay, you can make here contact also, no problem. Now this is the stick diagram representation, okay, of the this design. This is a stick diagram representation of this design. काही शंका असेल तर विचारा.
No query, sir.
Right, this is a stick diagram presentation of now what we are going to do is we are going to implement now this AND gate circuit, right? This AND gate you in the microwave. So now you have to remember this design. Okay, so we have parallelly connected PMOS A and B, and we have series connected NMOS, right? That forms the NAND CMOS. This is a NAND CMOS. Right, this is NAND. Now you have to remember this diagram, NAND CMOS. Okay, we will implement this same diagram with the help of microwave. With the help of microwave. Clear? Okay, now just remember this diagram. We will go to our simulation software and we will simulate there this same diagram. Okay, remember this equation also, A dot B bar. Okay, okay, now go to microwave. Okay, now screen is visible.
Yes, sir.
Okay, now we will start with the design. What we have to do, first we have parallelly connected PMOS and we have series connected NMOS. A and B, we are having two terminals. Now how to do that? Again go to this MOS generator. First we have to choose NMOS. You can choose, you can keep the 4 lambda is the minimum distance. You can keep any distance above 4 lambda. So I have chosen 5, no problem. So how many nmos we will require here? 2. See, with the help of this number of fingers, that means what, how many nmos you require, right? You can choose a different 2 nmos, or you can have the 2 nmos in a one design also. As here I have chosen the number 2. Now it will generate exactly 2 nmos. Now see, you are having the two gate terminals. Now how to identify this? This is a source of first nmos, gate of first nmos. This is the drain of first nmos. This is a source of second nmos, gate of second nmos, and drain of second NMOS. So likewise, you have to identify the terminals. Similarly, we will choose two PMOS. Okay, we will choose two PMOS. Generate device, click here. Now we are having the two PMOS. Place exactly above the NMOS. Okay, it is fine. We will move little bit there. Okay, now it is fine. Now this is the two PMOS. These are the two NMOS. Okay, now remember the design. What we have to do? We have to we have to short the source terminal of both PMOS, and we have to connect to the VDD. Okay, so select the metal. We will consider this is a source of first PMOS and this is a source of second PMOS, and these are the common drain of the two PMOS. Okay, so extend this metal over here. Extend this metal over here and see, try to maintain the same size and same shape, because you will get the less error. Okay, connect this. Okay, now we have shorted the source terminals of both PMOS. Now this remaining is the drain terminal of both PMOS. Okay, where we have to connect this drain terminal to the where we have to connect this drain terminal where we have to connect this drain terminal to the drain of next NMOS. That is, if you consider this A and this B, so you have to connect, you have to extend this, and you have to connect to this terminal. We will consider this of a NMOS. Okay, and you have to connect this, and from here only we are taking output, so you can extend this. Okay. Now this is a B, this is a B. So A of the PMOS and NMOS we have to short, right? So we have to short this A because here we have to apply the input also, right? Here we have to apply the input also. We will maintain a little distance. Just wait. Okay. Just hold for a minute. Hello. बाबू लेक्चर आहे तुला एक 10-15 मिनिटांनी करू. Okay, so we did this. Now what else? This is a drain of first, and this is a sorry, source of first NMOS. This is a drain of first NMOS, and this is again source of second NMOS. So we have to connect this to the ground. Okay. Now we have to apply the input and output. Okay. Let us apply input and output. First VDD you have to apply here as well as to the N well. Okay. This ground you have to apply here. Output you will get here. We will mention as a Y. Okay. And we have to apply now the two inputs A and B. So first we'll apply this A over here. We will mention A, okay, assign, and we will apply second one here as a B. You can keep the same name or you can give the different name also. Okay, you can change the speed, you can reverse the signal, anything you can do with this add clock. Assign, this is A and B. Why? Now everything is clear. Now before simulation, what is the required step? We have to check the design rule. Now see here, it is showing that the spacing between metal is, so we will just reduce the site and again check. Now see the error is gone. बघितलं कशी एरर येते ते की ह्या दोन मेटल मध्ये स्पेसिंग कमी झालं होतं. आपण ते एरर काढली की आता there is a no error. Okay. Now we will simulate this. Click on this. Now wait, you will get confused because we are having this inverter also, right? So what we will do, uh, we will delete this inverter. Okay. Okay. Is there any design check rule? No. Simulate. Now, what is the expected output in case of NAND gate? For 0, 0, this A is 0, B is 0. What you should get? 1. For 0, 1, you should get 1. For 1, 0, you should get 1. And for only 1, 1, you should get 0. बरोबर आहे की नाही? NANDचं ट्रूथ टेबल काय? एक्झॅक्टली अपोजिट ऑफ द AND गेट. AND गेटचं ट्रूथ टेबल काय? 0 0 0 0 1 0 1 0 1 आणि 1 1 1. आता तुम्हाला काय मिळणार आहे? 0 0 1 1 0 1 0 1 1 आणि 1 1 ला फक्त 0 मिळालं पाहिजे, राईट? बघूया मिळतंय का तसं. 0 0 you will get 1. 0 1 A is 0, B is 1, you are getting 1. But for A1 B1 you are getting 0. That means what you can say, our design is correct, right? Our design is correct, right? See, you got to learn this software, because if you want to go to the Velesa industry or some chip designing industry, so you may require this CMOS or this microwind is there, then cadence is there. It is somewhat similar to this microwind also. Then L-edit is there, mentor graphics is there. So these are the simulation software for the CMOS designs, right? So if you want to step into a Velesa industry, CMOS industry, you must know this software. Okay, how to simulate, what are the parameters, okay, how to check the output and everything. Okay, so that means you can say the our input is, or our simulation and execution is correct. Clear? ह्याच्यात काय अडचण?
No, sir.
Okay. Now, if I want to convert this NAND into AND gate, what I should do? Anyone? So, okay, fine. This is a NAND gate, no problem. See, you can label here also like this. Okay. If I will put here, I will label here as a NAND NAND gate assign. So here you will get this NAND gate. Okay. NAND gate. Now I have to change this NAND gate, right, into AND gate. What extra I got to do? काय करावं लागेल?
So inverter लावावा लागेल.
सिंपल. AND हे NAND च्या अपोजिट आहे. मग NAND च्या अपोजिट काय होणार? AND. Right? So if you if I add the inverter and I will give the output of NAND gate to the inverter, and if I will take the output from inverter, it will act as a AND gate. Okay, let us do it. Okay, immediately implement one inverter. So MOS generator. Now in case of inverter, I will require only one. Sorry, delete. Here now I will choose only one. Okay, inverter. Now I will generate PMOS over here. Let's assign. Okay, so okay, fine. Here also. Okay. Okay. Quickly make the gate of PMOS and NMOS shorted. It is misaligned, so we will exactly align this. Now it is aligned. Quickly drain off this both. You need to short. Okay, from this we are taking the output. Okay, now what else we need to do? Apply VDD here, also to the N well. Apply ground to the this. Apply this visible no. Now here I will give as a output. Sign. Okay. Now what I have to do? I have to apply the output of this NAND gate AND gate. Okay. So how I will do? Just simply extend this polysilicon little bit over here and extend this metal. Just wait. Or first I will do this. I will extend this metal and then I will extend polysilicon. Now how to connect this? So now here you have to use the contact. See, contact metal to poly. That means this is a poly, this is a metal. You have to use this contact. You have to place here. Now means you have now connected this output to the gate of this inverter. Okay, check design rules. So you can this contact design rules actually you can omit. Okay, this extra poly surrounding contact is less than 2 lambda. So this you can actually ignore, or you can do this also. Okay, no problem. So metal, and from this you can connect to this. No problem. You can ignore this, only contact rule. Okay, now A, B, Y, and this is the output, means what? It is the output of NAND gate. So now we will check through simulation. Okay, now check. First output is of AND gate, and this Y is of NAND gate. Okay, now what is for 0 0? It is 0. For 0 1 it is 0. For 1 0 it is 0, and for 1 1 it is 1. And exactly reverse is the case for NAND gate. म्हणजे AND गेटचं जे आउटपुट आहे त्याच्या एक्झॅक्टली अपोजिट NAND गेटचं येणार. म्हणजे बघा, जिथं AND गेट साठी 1 आहे तिथं NAND गेट साठी 0 येणार, आणि जिथं AND गेट साठी 0 आहे तिथं NAND गेट साठी 1 येणार. That means what? Our entire design is correct. Our entire design is correct. समजलंय का?
Yes, sir.
Everyone through with this? समजलंय का सगळ्यांना? Everyone clear with this?
Yes, sir.
Okay, fine. So in this practical, we have covered the 3 practicals, right? Introduction to CMOS and microwind. Second one is CMOS inverter, and our third practical is implementation of NAND and AND gate using CMOS. Okay, so we have covered the 3 practicals. So in next practical session, we will proceed with the remaining one.
Okay, sir.